Hello friends, welcome to UGC EPG Pathshala. I am Swati Katyar, Senior Research Fellow, Birla Institute of Scientific Research, Jaipur. Today we will discuss about the topic unsupervised classification. We will start with the introduction. Image classification refers to the process of extraction of information from the satellite image. The purpose of the image classification is to categorize all the pixels in the digital image into one of the several land use classes or themes. In order to make use of the multitude of digital data available from satellite imagery, it must be processed in a manner that is suitable for the end user. For many projects, this process includes categorizing the land into various use functions. Depending on the interaction between the computer and interpreter during classification process, there are two types of classification. These two main categories used to achieve classified output are called supervised classification and unsupervised classification. Now we will discuss about the techniques. Unsupervised classification, that is commonly referred as clustering, is an effective method of partitioning remote sensor data in a multispectral feature and extracting land cover information. Compared to supervised classification, unsupervised classification normally requires only a minimal amount of initial input from the analyst. This is because clustering does not normally require training data. Then the process where numerical operations are performed that search for natural grouping of the spectral properties of pixels as examined in the multispectral feature space. The clustering process results in a classification map consisting of m spectral classes. The analyst then attempts a posteriori to assign or transform the spectral classes into thematic information classes interest, that can be forest or agriculture. In unsupervised classification, the software does most of the processing on its own, generally resulting in more categories than the user is interested in. This is the point where the user has to make decision on which categories can be grouped together into single land use category. In either case, additional image processing may be used to determine which method is better for a given situation. It must be kept in mind that maps are simple attempts to represent what actually exists in the world and are never completely accurate. The image used in this demonstration is Landsat 5 thematic mapper scene. Ground resolution for this image is 30 meters. Landsat TM records the data in 7 different bandwidths. These bandwidths cover part of visible, infrared and thermal infrared region of an electromagnetic spectrum as shown in the table number 1. This composition window is a window from Landsat image. This scene is centered on a Perry Reservoir located in a Jefferson County, northeast Kansas, and is shown in the natural color in figure number 1. This composition particularly shown is from the same Landsat scene shown using band 3, 4 and 5 respectively, displaying in a BGR. In this composition, vegetation appears in bright green, while some of the agriculture field still with a good portion of a bare soil are displayed in a pink color. Also, there is a considerable amount of grassland in the scene that is displayed with a combination of the green and pink colors. By examining the second composition, the land use patterns can be seen quite well. A good portion of the bare soil is located along the Kansas River in the bottom part of the image. There is also the presence of tilled field located throughout the image with larger concentration in the northwest corner. From the enlarged image, numerous small lakes and ponds can be identified in the dark blue. Most of these small ponds can be seen in the grassland areas. These ponds are most likely located in the pastures and used as watering holes by the cattle. Other important land features include the forested areas as well as the dam and outflow of the Perry Reservoir. The forest sprawls outward from the reservoir and follows a small drainage, while the man-made dam lies in the south end of the Perry Reservoir and releases water into Kansas River. In order to get this image into more usable format, several attempts were made to classify the land uses of the separate categories. Unsupervised classification, the idea. An attempt made to classify the various land uses in Idrisi was done using unsupervised classification techniques. Unsupervised classification techniques do not require the user to specify any information about the feature contained in the images. This example was conducted using the isoclass module in idrissi. With the isoclass, the user simply identifies which band idrissi uses to create the classification and how many classes to categorize the land cover feature into. Again, Landsat TM bands 1 to 5 and 7 were used. The resulting classified image is shown in the figure number 3. At this point, the image is difficult to interpret. Looking to the image and classified output, the decisions need to be made to convert spectral groups into feature or thematic classes. To make these decisions, other material and knowledge of the area are useful. Ground truthing what is seen in the digital image with what was actually present at the time the image was recorded makes this task more efficient and more accurate. If this knowledge is not available, scientific reasoning may be used to group the various categories together into land use categories. In the demonstration example, 6 land cover types were identified from the 16 categories as shown in the figure number 4. Area of each category can be calculated through the software as shown in the table number 2. The image below shows a close-up of the dam and the outflow area of the Perry Reservoir and in the figure number 5. Again, it can be seen that areas classified as agriculture fall in areas where agriculture is not likely present. Similar examples can be found throughout the image. There are two main methods of the unsupervised classification clustering, that includes k-means clustering and isodata clustering. Firstly, we will discuss about the k-mean clustering. K-means is one of the simplest unsupervised learning algorithm that solve the well-known clustering problem. The procedure follows a simple and easy way to classify a given data set through a certain number of clusters. Assume it to be a k cluster, fixed priori. The main idea is to define k centroid, one for each cluster. These centroids should be placed in a cunning way because of different location causes different results. So the better choice is to place them as far as possible from each other. The next step is to take point belonging to a given data set and associate it to the nearest centroid. When no point is pending, the first step is completed and an early grouping is done. At this point, we need to recalculate k new centroids as the barycenters of the cluster resulting from the previous step. After we have these k new centroids, a new binding has to be done between the same data set points and the nearest new centroid. A loop has been generated. As a result of this loop, we may notice that the k centroids change their location step by step until no more changes are done. In other words, centroids do not move anymore. Finally, this algorithm aims at minimizing an objective function, in this case a squared error function as in this equation given below. The algorithm is composed of the following steps. Place k point into the space represented by the object that are being clustered. These points represented initial group centroids. Again, each object to the group that has the closest centroid. When all the objects have been assigned, recalculate the position of the k centroids and repeat the step number 2 and 3 until the centroids no longer move. This produces a separation of the objects into groups from which the metric to be maintained and can be calculated. Although it can be proved that the procedures will always terminate, the k-means algorithm does not necessarily find the most optimal configuration corresponding to the global objective function minimum. The algorithm is also significantly sensitive to the initial randomly selected cluster center. The k-means algorithm can be run multiple times to reduce the effect. K-mean is a simple algorithm that has been adapted to many problem domains. There are two main types of scheme to use k-mean algorithm to classify the data. We will discuss about the scheme number 1. The one method used is to separate the data according to the class labels and apply k-means to every class separately. If we would have two classes, we would perform k-means twice, once for each group of data, and at the end we require to set a prototype for each class. When we have a new data point, we put all of the prototypes together and find which one of the closest to the new data point. This prototype is associated with a class because the prototypes are created by clustering each of the data individually. The class of this prototype is taken as the class of the new data point. Scheme 1 of using k-means clustering is to training data in each class separately using r prototypes per class. assign a class label to each of the k cross r prototypes, classify a new feature vector x to the class of the closest prototype. Below is the result from the text using the scheme and is shown in the figure number 6. There are 3 classes, green, red and blue. K-mean clustering is applied using 5 prototypes for each class. We can see the below that for each class the 5 prototype chosen and is shown by the filled circles. According to the classification scheme, for any new point among these 15 prototypes, we would find one closest to this new point. Then, depending on the color code of the prototype, the corresponding class will assign to a new point. The black lines are classification boundaries generally by the k-means algorithm. Specifically, these are the classification boundaries induced by the set of prototype based on the nearest neighbor. The decision boundary between any 2 prototypes based on the nearest neighbor rule is a linear. Every prototype occupies same region in a space. The region around each prototype is sometimes called Voronoi region and is bounded by the hyperplanes. Because we have more than one prototype for each class, the classification boundary between 2 classes is connected segments of the straight line, which gives a zigzag look. Now we will discuss about the scheme number 2. The second scheme of the classification by k-means is to pull all the data together and perform k-mean once. There is no guarantee that the points in the same group are of same class because we conduct k-mean on the class banded data. To associate a prototype with a class, we count number of data points in each class that are assigned to this prototype. The dominant class with the most data point is associated with the prototype. During the classification of new data point, the procedure then goes in the same way as shown in the scheme number 1. Now we will discuss the steps for the scheme number 2. The very first is apply k-mean clustering to the entire training data using m prototype. Then for each prototype, count the number of samples from each class that are assigned to the prototype. Associate the prototype with a class that has the highest count and then classify a new feature x to the class of the closest prototype. Now we will discuss about the second type, that is the isodata clustering. The iterative self-organizing data analysis technique, that is the isodata, represent a comprehensive set of heuristic, that is rule of thumb procedure that have been incorporated into an iterative classification algorithm. Many of the steps incorporated in the algorithm are a result of the experience gained through the experimentation. The isodata algorithm is a modification of the k-mean clustering algorithm, which includes the very first merging clusters if there is separation distance in the multispectral feature space is below a user specified threshold, and b, the rules of splitting a single cluster into 2 clusters. Isodata is iterative because it makes a large number of passes through the remote sensing data until specified results are obtained instead of just 2 passes. Isodata does not allocate its initial mean vectors based on the analysis of pixels in the first line of data the way the 2-chain algorithm does. Rather, an initial arbitrary assignment of all Cmax cluster takes place along an n-dimensional vector that runs between very specific points in a feature space. The region in a feature space is defined using the mean and the standard deviation of each band in the analysis. This method of automatically seeding the original Cmax vector makes sure that the first few lines of the data do not bias the creation of clusters. Isodata is a self-organizing because it requires relatively little human input. Typical isodata algorithm normally require the analyst to specify the following criteria: Cmax, that is the maximum number of clusters to be identified by the algorithm. However, it is not uncommon for fewer to be found in the final classification map after splitting and merging take place. T, the maximum percentage of pixel whose class values are allowed to be unchanged between iterations. When this number is reached, the isodata algorithm terminates. Some datasets may never reach the desired percentage unchanged. If this happens, it is necessary to interrupt processing and edit the parameter. Now M, the maximum number of times isodata is to classify pixels and recalculate the cluster mean vectors. The isodata algorithm terminates when this number is reached. Minimum number in the cluster % if a cluster contains less than the minimum percentage of members, it is deleted and the members are assigned to an alternative clusters. This also affects whether a class is going to be split. The default minimum percentage of member is often set to 0.01. Now, maximum standard deviation, that is sigma max, when the standard deviation for a cluster exceeds the specified maximum standard deviation and the number of members in the class is greater than the twice of the specified minimum members in a class, the cluster is split into two clusters. The mean vector for the two new clusters are the old class centers plus minus 1 of the standard deviation. Maximum standard deviation value lies between 4.5 and 7 are typical. Split separation value. If this value is changed from 0, it takes the place of the standard deviation in determining the location of a new mean vector plus and minus the split separation value. Minimum distance between cluster. The cluster with a weighted distance less than this value are merged. A default of 3 is often used as shown in the figure number 7 below. Hope you have enjoyed this lecture. Thank you.